Alright, so in this video I'm going to be explaining another important article with the title Affinity Aware Graph Networks. This paper in 2022 by DeepMind. Graph neural networks have emerged as a powerful technique for learning on relational data, owing to the relatively limited number of message passing steps they perform, and hence a small receptive field. There has been significant interest in improving their expressivity by incorporating structural aspects of their underlying graph. In this paper, we explore the use of affinity measures as features in graph neural networks, in particular measures arising from random walks, including effective resistance, hitting, and commute time. We propose message passing networks based on these features and evaluate their performance on a variety of node and graph property prediction tasks. Our architecture has lower computational complexity, while our features are invariant to the permutations of the underlying graph. The measures we compute allow the network to exploit the connectivity properties of the graph, thereby allowing us to outperform relevant benchmarks for a wide variety of tasks, often with significantly fewer message passing steps. On one of the largest publicly available graph regression datasets, this OGB, we obtained the best known single model validation at the time of writing. So we propose the use of these affinity measures as features in graph neural networks to circumvent this limitation. So we consider statistics that arise from random walks like hitting time, commute time. We present means of incorporating these statistics as a scalar edge feature in message passing neural network. Additionally, we present a set of vector-valid resistive embeddings that can be incorporated as node or edge feature vectors in the network. So we define several natural properties of graph that arise from a random walk. A random walk on G starting from a node U is a Markov chain on the vertex set V such that the initial vertex is U. And at each time step, one moves from current vertex to a neighbor chosen with probability proportional to the weight of outgoing edges. So we will use pi to denote this stationary distribution of Markov chain. We know for undirected graph, this is the stationary. D sub u in the denominator, if you look at that, is the weighted degree of node u. And m is the denominator here, is the sum of edge weights. The hitting time, by the way, as I said, you go and then come back. So the hitting time of going and then come back, if you add them up, you get the commute time. Effective resistance, we calculated here, and it's related to this minus pseudo inverse. So calculation of this is computationally expensive. There are many methods. Solving linear systems. It's a historical problem by Spielberg in 2005, I guess, and then 2008 he wrote a great paper. But this is just one approach. Effective resistances allow us to define the resistive embedding. I've explained effective resistance in my playlist for approximation algorithms. So let's carry on. As I said, you just need to calculate this one. But do you think, what is this? This is the pseudo inverse. This is the pseudo inverse. This is what make it a challenge for large graphs. For any pair of nodes, we have this because first we say that the effective resistance embedding is just related to to this, and then the distance for any pair u and v, it could be anything. Doesn't need to be have an edge too. So it is the distance, the L2 norm, is equal to resistance embedding between u and v. And then they say they define the mean effective resistance embedding. So using effective resistance, they define the mean of that. Also, the definition of heating time radius is important. The maximum of all heating times between all pairs u and v. Any pair u and v that you imagine, if you calculate the maximum of all possible things, it becomes H max. It is has an important topological properties. It restricts the graph to a particular distribution. So this is interesting to look like this. If you put constraint on heating time radius, it means that you are putting restriction on the distributions on all graphs. Do you see how powerful it is? For any node, we have this relationship. So the distance between effective resistance embedding and the mean of that is upper bounded by H max. Do you see how effective resistance is connected to heating time radius? It is gorgeous. So here there is another theorem that message passing neural networks that make use of any one of effective resistances, heating times, resistive embeddings are strictly more powerful than WL1 test. Even heuristically, you understand why that should be the case. Because you are creating some kind of hierarchy, some structure, some order on the set of nodes. So that makes it much more powerful than something that is with any permutation, it becomes anything else. We now show that GNNs with affinity-based measures can distinguish between a node and a node VJ. So we note that the heating time from A to B depends on the isomorphism classes of A and B. Let's go back to this. So we also want to talk about shortest path distance. It is interesting to compare the use of effective resistance with shortest path distances. The most direct comparison of our effective resistance based would be to use SPDs, shortest path dependent distances, as edge features in the message passing neural network. However, note that SPDs along graph edges are a trivial feature, unlike effective resistance, which is still incorporate useful information. So they are trivial feature. So it means that we infer that the author wants to say that effective resistance has a more important effect, and it has a better representations of the topology of the graph in comparison to shortest paths. So an alternative to edge features would be to use SPDs to a small set of anchor nodes as features in a message passing neural network. A dense featurization incorporating shortest paths between all pairs of nodes. We empirically compare our models to message passing neural networks that use approaches A and B. So reducing dimensionality of resistive embedding. If you look at my first video on my playlist for graph embedding, you saw that I talked about this important Johnson-Linder-Strauss lemma that says that let's have a set of endpoints. So we have endpoints, and then let these alphas be fixed linear combination. And suppose pi is a k by d matrix whose entries are chosen IID from a Gaussian. And then consider this variable. We can show that with probability 1 minus linear, we have this relationship. So it is upper bounded and lower bounded, we can say, with this. And using the triangle inequality, we can see that the inner products between fixed linear combinations are preserved up to some additive error. So we can compute the heating times very fast, because if you consider this quantity, this heating time, we will use this quantity as an approximation of the actual heating time, which is very hard to compute. So this is just an approximation. And you see, for heating time, we just use the resistive embedding and the mean of that here. And then there are some lemmas that connects heating times to the effective resistance embedding. And their experiments show that, so let's go through these. We provide encoders F sub n, F sub e, and F sub g that transform the inputs into a latent space. Our message passing neural network then performs several message passing steps, contains all of the latent at a particular processing. This process is iterated from T steps, recovering final latents. These can then be decoded into node, edge, and graph level predictions using analogous decoder functions. Generally, FG are MLPs, while we use a message passing neural network update rule. It computes message vectors to be sent across the edge, then aggregates them at the receiver nodes like this. The message passing functions and the update are both MLPs. So for graph tasks, for example, if you look at graph attention, graph convolution, message passing neural network, you see for different tasks, you see the log of MSE on PNA test dataset. And these are test mean average precision for this performance for various model depth. So random features is another important for graph. We call it graph random features that I will explain in several videos. It's important. Of course, this one was invented in 2005 by Ali Rahimi and Resht, and it's very important. Then a genius guy, generalized this to graph random feature, which is also related to the kernel, the general graph kernel, which is amazing. Everything becomes a special case. So that's another video. So we propose a message passing network based on random walk, based on affinity measures. And this is important. Our proposal carefully balances theoretical expressive power, empirical performance, and scalability to large graphs. This is very challenging.